Let's do one more example with the F distribution. This time we're going to do an interval estimation problem, just a formal one. So let's suppose we have two normally distributed populations. Normally distributed populations. We take samples of size, let's just say 21 and 36, respectively. And we'd like to obtain a 90% confidence interval for the ratio of their variances. So these populations, they have normal distributions, but the parameters of these normal distributions are unknown. They have some unknown means and variance. And what we do is we can measure, of course, the sample variance. And we want to know how good is our approximation, what is our 90% confidence interval for the ratio of the actual variances. So, for example, like suppose we measure an actual measured sample variance of 9 for the first population, and for the second we measure an actual variance of 20. So pretty close to ratio of a half, right? We're asking like what is sigma 1 squared over sigma 2 squared, and of course it's going to be close to a half, but it could be, you know, widely ranging. We're not sure what the difference is. We're going to find a 90% confidence interval. Okay, so let me just introduce the following useful notation, which you'll find in tables in the back of many statistics books. So if I were to write f sub alpha nu 1 nu 2, this is the number such that if I looked at a cumulative density function for an f variable with nu 1 and nu 2 degrees of freedom, then the probability that f variable is less than or equal to this value, f of alpha nu 1 nu 2, is 1 minus alpha. Or in other words, the probability that an f variable is at least this large is alpha. So there's only alpha left on the tail of the distribution, if you will. Okay, so for our problems, it's going to be useful to keep in mind a couple of numbers. So I'll just set f for the time being to be the number 0.05, so the 0.05 or 95% value for the f distribution with 20 and 35. 20 and 35 being 21 minus 1 and 36 minus 1. And let me let f prime be f of 0.05, 35, and 20. So for right now, I haven't told you why I'm going to use these numbers, but I'm just going, I will use them, and I don't want to keep writing them over and over. So I'll just put them like that. So our goal, or strategy, if you will, is we're going to find random variables. We'll call them, let's say, R small and R big, such that these are going to, of course, depend, these are random variables, so they're going to depend on what we read in our sample. So these are going to depend on S1 squared and S2 squared, our sample variances, such that if we were to look at the probability that, that sigma 1 over sigma 2 squared is at least R big, then this is actually going to be 5%. And the probability that sigma squared over sigma 2 squared is less than R small is going to be 5%. So our goal is to find these numbers R big and R small, because if we did, then we would know that the probability that R small less than sigma squared over sigma 1 squared over sigma 2 squared is less than R big would be 90%, right? Because we're saying, you know, for this inequality to hold, We just don't want this to be bigger than that, 5% chance of that. We don't want this to be smaller than that, 5% chance of that. And so that's what we're actually looking at. So we need to basically solve these two equations. We need to find random variables r big and r small such that those things will hold true. So let's just write what we know based on the definition of these f's. We have a particular f variable with these 20 and 35 degrees of freedom, which is the sample variance number 1 divided by the population variance number 1 divided by s2 squared over sigma 2 squared. So this is an f variable with, so s1 was a sample size of 21, so this is with 20 and 35 degrees of freedom. And similarly, f prime, which is the reciprocal of that, is an f variable with 35 and 20 degrees of freedom. Okay, so what do we know? Well, by definition of these numbers that we just brought up, these f and f prime, we know that the probability that the random variable f is at least f is 5%. That's because of this 0.05. And similarly, the probability that f prime is at least little f prime is also 5%. Okay, so let's just take these things that we have by definition and just manipulate them a bit. So this says the probability of s1 over sigma 1 squared divided by s2 squared over sigma 2 squared is at least f is 5%. Now, what I would like to get is some constraint on this quantity sigma 1 squared over sigma 2 squared. So I'm basically going to take this and I'm going to solve for it in this inequality. So rewriting this, we have s1 squared over s2 squared, sigma 2 squared over sigma 1 squared. Sigma 1 squared is bigger than f with a 5% chance. And let me move that sigma 1 over sigma 2 squared object to one side, divide out by the f, and I get the probability that 1 over f, random variable s1 squared over random variable s2 squared, is bigger than sigma 1 squared over sigma 2 squared, the parameter of interest, is 5%. And so this thing we find is, what are we saying? It's usually not bigger, right? There's only a 5% chance that it's bigger than my random variable. So my random variable, wait, did I say that right? There's, so we're saying there's a 5% chance that this is bigger than this. So usually our random variable is going to be bigger than, there's a 95% chance that sigma 1 squared over sigma 2 squared is bigger than 1 over f s1 squared over s2 squared. So that means that this is my r small. It's the lower bound of my confidence interval. Let's actually just go ahead and compute what f is. So remember, f is 0.05, 20, 30. And it represents how far out I have to go in an f distribution with these 20 and 35 degrees of freedom, so that when I get this far, there's 0.05 on the right under my distribution function, which means that to the left, there is 95%. So I'm going to look this up in R. We can look it up in the table in the back of the book. But looking it up in R, we're going to do it a little bit backwards. So hello, R. So this is, we're going to use the quantile function. And for this, we tell it how far do we have to go to get 95% under the f variable. So that qf is q for quantile, f for the f distribution. 95% is, how much we're going to get up to there. And then we're saying with 20 and 35 degrees of freedom. And the answer is 1.88-ish. So I made a little typo there. That's a 35. And the answer is 1.88. And so what do we get for our R small? We get, so our measured value of R small is, so we have, of course, this constant 1.88. That's just a fixed constant. But then times our actual measured values of S1 squared and S2 squared, we get 1 over 1.88. Measured value is 9. Measured value is 20. So let's ask R again. If I said 1.88, and I multiply that, let's say 1 divided by 1.88, and let me multiply that by 9/20ths, and we get 0.24-ish. Okay, so what that says is, of course, we checked originally that there was, that we expected the ratio of these variances to be about a half. It was 9/20ths in our measurement. And we say, well, we're 95% sure that it's at least 0.24. It's going to be hopefully close to a half, but at least we're 95% sure that it's bigger than 0.24. Now let's do the other side. So for that, we'll be using this expression right here. So here we have a random variable which has an F distribution with 35 and 20 degrees of freedom, going the other way. And so we say the probability that f prime is at least a little f prime is 5%. That was the point of this little f prime. And our particular capital F prime variable is the reciprocal of that other guy. So it's the S2 squared over sigma 2 squared, S1 squared over sigma 1 squared. So it's that thing bigger than little f prime. And now let me break that fraction up a bit so that I can extract from it my parameter of interest, which is this sigma 1 squared over sigma 2 squared. So I'm really interested in this particular parameter and bounding it. So I'm going to solve this inequality for it and keep it on this left-hand side. And I get that this is at least S1 squared over S2 squared, f prime. And so that means that there's a 5% chance that my guy is bigger than that, and therefore a 95% chance that my parameter is no more than that. And so generally this is above it. This is my R big, my random variable that 95% of the time is above the parameter of interest. Our measured value for R big is going to be f prime times little s1 squared over little s2 squared, f prime times 9/20ths. But now again, we have to ask R what actually is f prime. So again, here we are back at R, and it's the quantile function for the f distribution up to 0.95, but this time for 35/20. And we find that it's about 2. So this is roughly 2, no, not 20, 2. And so we have that our, f prime is about 2, so f prime times 9/20ths. And so we find 18/20ths, or 9/10ths. So that means that our confidence interval, this is a 90% confidence interval for the ratio of the variances, is going to be, what was that first measurement that we got? 0.24. 0.24 is less than sigma 1 squared over sigma 2 squared. I was sloppy and I lost some of my significant digits probably, but let's just say 0.90. That's pretty close. And that's our 90% confidence interval. Great.